to do this topic before getting into the actual matter lessons on Monday is because this is going to be important later on in the year when we have to work with things possibly with stoichiometry or even with our unit conversions. When we get those really big numbers or really small numbers with a lot of zeros, and it can be a pain to write out, this gives us a way to write an answer without all of those zeros or without a number that's really big. And that is going to be scientific notation. What I mean by scientific notation are the times that you see a number like 3.3 times 10 to the fifth, or 2.6 times 10 to the negative seventh. When you see these numbers times 10 to an exponent, and the exponent is either positive or negative, this is what we call scientific notation. And what this is it's going to be used, this is used as a way to write very small or very large numbers. We're going to very small or very large numbers. With the correct number of sig figs. So we're going to use this to write very big, very small numbers with the correct numbers of sig figs and make numbers more manageable. We're going to make numbers more manageable. And again, that's those really big, really small numbers. With scientific notation, we've got to pay attention to the number of sig figs. We're going to have to pay attention to the number of sig figs when we're writing in scientific notation. So let's just look at an example of what I mean. The first number we're going to look at here, and let's change colors. Let's go to this little, actually, for Breast Cancer Month, let's do the bright pink. We're going to go to 93 billion. Okay, so we have 93 billion here. And if you would have watched the video yesterday, you would have seen that is the net worth of Bill Gates. I wish we all had that much money in our bank accounts. But with this number here, even though it's a really big number, it only has 2 sig figs. Sig figs being the 9 and the 3. The rest of these are not significant because they are trailing zeros. So these are trailing zeros and they're not significant. So that's a really big number to write, and it sometimes can be a pain to write that out over and over and over again. So what scientific notation would be is we're going to move a decimal place. We're going to move a decimal place. Now, you'll say to me, Mr. Krupa, there is no decimal place. I know there's nothing written there, but there is an understood decimal place. That decimal place is going to be right here at the end, where you can't see it. It's kind of the same concept of if you, in math class, if you have x, x is just x, but it's understood to mean the same thing as 1x. You just don't write the 1. The same concept here where that decimal place isn't written if it's a whole number, but it is understood that it's there. And what we're going to be doing is moving that decimal place. We're going to move that decimal place and we're going to go to the left, actually. We're going to move that decimal place to the left and we're going to use, let's go with a red there. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what this number actually turns out to be is 9.3 times 10 to the 10th. Another example would be something along the lines of 0.0000076. So we have a lot of zeros there, so we have all these zeros in this. In this entire number, there are only 2 sig figs. The only sig figs are the 7 and the 6 because all of these zeros are leading zeros, and they are not significant. So what we'll be doing with this number is moving the decimal place to the right. So 1, 2, 3, 4, 5, 6, 7. We're going to move it 7 times. And we're going to get the answer of 7.6 times 10 to the negative 7th. So we're looking at this, so we have 2 numbers here, one with a positive exponent, one with a negative exponent. Whenever you're going to write these, what you're going to find is, in general with scientific notation, whenever you have the decimal place, and we have a decimal place here, and we move it to the left, if we're going to the left, the number after you write it is going to have a positive exponent. If you have a decimal and you move it to the right, the number is going to have a negative exponent. And again, you come up with the question of, Mr. Krupa, but we've learned on the number line, if you go to the left, the number is negative. If you go to the right, the number is positive. So why is it opposite of what we've always learned? And that is absolutely true whenever you think about it, where the decimal place actually would be. What I mean by that, for 7.6 times 10 to the negative 7th, if we want to get back to the original number, take it out of scientific notation, the decimal place would be going to the left. That negative here is saying we're going to move the decimal place to the left, going towards the negative whenever we take it out of scientific notation. And we know how many places to move the 0 because of this part right here. Because what this means is, to get it back to the original number, we're going to have 10 times 10 times 10 times 10 times 10, 1, 2, 3, 4, 5, 6, 7. 10 times 10 times 10 times 10 times, 7 times, because 7 times. And after we do that, we know that's how many zeros we're going to get, and because it's a negative number, it's going to go to the left. And we get back to 0.00000076 because we moved the decimal place 1, 2, 3, 4, 5, 6, 7 places back to get to the original number. The same is going to apply over here to the 9.3 times 10 to the 10th. If we want to get the number back to the original, we follow what this says here. The exponent here is positive. So we know that to get to the original number, we're going to move the decimal place back to the right, which would follow the rules for the number line. So this one would be 10 times 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 10. I think 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we have 10 times 10, 10 times. And if you take that times 9.3, so we have 10 times 10, 10 times. You're going to do exactly what that says, 10 to the 10th. If you had 10 squared, it would be 10 times 10. If you had 10 to the third, it would be 10 times 10 times 10. And then you would multiply by 9.3, and it gets you back to your original number. That's what scientific notation is saying. It's telling you how the decimal place is moved around. And it's just giving you an easy way to write this large numbers in a smaller way. So it gets easier with practice. So let's take a look at a few numbers here. If we had the number 530,000, what would this number be in scientific notation? The correct answer is going to be 5.3 times 10 to the 5th, because we're going to go 1, 2, 3, 4, 5. We moved it 5 places, so we have an exponent of 5, and there's only 2 sig figs. So we got to make sure we have 2 sig figs when we write it in scientific notation. Let's do another one here. Let's go 4,000. Write that in scientific notation. Well, that comes out to be 4 times 10 to the 3rd. 1, 2, 3. And it's only 4 because I got 1 sig fig here, 1 sig fig here. Let's do one more. Let's go 30,300. Write that one in scientific notation. Well, this actually comes out to be 3.03 times 10 to the 4th. 1, 2, 3, 4. And we see there's 1, 2, 3 significant figures because this 0 right here is a trapped 0. So 3.03 times 10 to the 4th. So we had 3 sig figs here, 3 sig figs here. We got to keep those number of sig figs. Now let's go to the other side. Now let's go the other way. Let's say we have 0.0000000604. Write that number in scientific notation. What you get is 6.04. 6.04, we're going to move that up actually. 6.04 times 10 to the negative 9. Because 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you haven't noticed yet with scientific notation, every time we write this, there's one number in the front, one number in the front, one number in the front, one number in the front. What I mean in the front is to the left of the decimal. One number to the left of the decimal, one number to the left of the decimal. Anytime you write scientific notation, at least for now, please try to have one number to the left of the decimal. Now sometimes, like this example here with the 4, you only have one whole number because that's all you got. You can't add another 0 to it because I'm going to go back to that one example here with the 4,000. I'm going right here. If we wrote this as 4.0 times 10 to the 3rd, what happens is right here are 2 sig figs. This is only 1 sig fig, and this is only 1 sig fig. If we write it as 4.0, we accidentally added an extra sig fig we can't have there. So that would be wrong. We've got to make sure we keep the number of sig figs. So let's do one more here. We're going to do 0.0009. 0.009. Write that one in scientific notation. What you actually get is 9 times 10 to the negative 4th. 1, 2, 3, 4. 9 times 10 to the negative 4th. We want that whole number there. So this is going to be scientific notation. And again, we have, if I could make it right, we have 1 sig fig, 1 sig fig. So this is your scientific notation notes. We will be applying this to everything that goes along with unit conversions. I had a brain fart there, I apologize. So this will be applied to our unit conversions. If you have any questions on this topic, please feel free to reach out to me. Thank you everybody and have a wonderful day.